So limit laws are what allow us to find limits when our functions look like equations by evaluating. So we've already practiced this a little bit just kind of by doing it. So now we're just going to show why we're allowed to. So let's start with two basic limit laws. And so the first one is the limit of a constant function. So a constant function, remember its graph is a horizontal line. So the limit as x approaches a of c, c is our constant function, is equal to c. Okay, so if you think about that graphically, right, so we'd have our axes, we have some value c, right, that's equal to our function. So here's our equation, y equals c. And we're saying that as x approaches a, so grab some arbitrary x value and call it a. So as you head towards a from both directions, your y value stays at c. Okay. And then the other one, the other basic function is the limit of the identity function. So the identity function is, right, y equals x. Whatever you put in, you get out. So if you do that graph, so I'll just do my axes here in pen and then just a, right, so that's the diagonal line with a slope of 1 going through the origin, right, there's the identity function. So again, grab some arbitrary x value, call it a, get on your graph. Okay. So the limit of this function, so again, as you go from either side of a towards a, right, as you're walking in that way, your y values, right, are a, right, because whatever you put in, you get out. Okay, so if we can believe these two basic limit laws, then what we do with the rest of these is just build off of that. So this is going to be a lot like the algebra of functions section from an algebra class you might have had. So here's where we go. I'm going to, there's a lot of words in here, and again, it's for the desensitization element. Because a lot of calculus, we have these caveats. So this is true as long as you meet these conditions. So just getting used to reading through those conditions is important. So here we go. We're going to let f of x and g of x be defined for all x that aren't equal to a over some open interval containing a, right? So that means we're just some chunk of x values that a is included within. These two functions f and g are defined. Okay. Now assume that capital L and capital M, so assume L and M are real numbers, so they're just numbers, and the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is M. Okay, so let's go over our caveats again. Your functions, f and g, two separate functions, they're defined, right? So nothing weird happening in the vicinity of x equals a, and the limit of f is L and the limit of g is M. Okay, so that's where we are. So the sum law, the limit as x approaches a of f of x plus g of x, well, that's the limit of f of x as x approaches a plus the limit of g of x as x approaches a. Right, so the limit of a sum is the sum of the limits. Cool. And the limit of f is L, and the limit of g is M. Okay, so we can, if we have the limit and we have, right, two terms that are added or two functions that are added, we can just find each individual limit and then add those together. Okay. The difference law. Right, so the limit as x approaches a of f of x, difference, right, subtraction, minus g of x. So the limit of a difference is the difference of the limits. Right, it's just a great opportunity to write limit a lot. So I know you know what comes next, right? Just L minus M, the limit of f minus the limit of g. Constant multiple law. So if you have the limit as x approaches a, so c is going to be my constant, of c times f of x, then that constant multiple can come out to the front. So that's c times the limit of f of x as x approaches a, but the limit of f of x as x approaches a, right, that's equal to L. So this equals c times L. I'm going to hit the focus button real quick. I'm hoping that wasn't out of focus this whole time. Okay, product law. So if we have the limit, again, x approaches a, so not constant multiple, but this time we'll go ahead and multiply f of x times g of x. That's right. Usually things like this don't happen with multiplying, so you have to be a little bit careful, but this time it does. So the limit of f of x times the limit of g of x. So L times m. So the limit of the product is the product of the limits. Quotient, I know you can do it, right? Nothing tricky. In fact, for all of our limit laws, I don't have, well, okay, I have some caveats down here, right? But up until our root law, really, we don't have any caveats. It just works, right? You can add, subtract, multiply, or divide your limits. What do we have? F of x over g of x. So the limit of the numerator divided by the limit of the denominator. So L over m. Oh gosh, I should probably do something. Okay, this one has a caveat. As long as what? Yeah, m is not 0. We still can't divide by 0. Well, okay, this is the year that we find out how we deal with division by 0. Okay, so there'll be, we'll have some different strategies depending on what's in the numerator. Okay, power law. If I have the limit as x approaches a of f of x, and that's raised to, say, the nth power, I can, right? So exponentiation, right, that's just repeated multiplication, and since we have a product law, right, that's going to work here. So that means I can take the power of the limit and raise that to the power. Again, inside your parentheses, that's all equal to the real number L. So L to the nth power. And then our root law. So I wrote this one out because I was afraid I'd forget one of our caveats. So if we have the limit as x approaches a of the nth root of f of x, then that's equal to the nth root of the limit. And the limit, remember, is L, so the nth root of L. Remember, roots are just a version of a power law. So this is true for all L, that's supposed to be if n is odd, and for L is greater than or equal to 0, if n is even, and f of x is greater than or equal to 0. So just some caveats on, right, we only take even roots of non-negative numbers. Okay. So, oh, and then the other one, we only get out positive numbers if we're doing even roots. Okay, so those are the two caveats for the root law. Okay, so here we go. So since polynomials and rational functions are combinations of the constant function and identity function, so combinations, addition, subtraction, multiplication, division, powers and roots, right, of the constant function and identity function up top, then we can use these rules, right, to evaluate limits by substitution. So do not try to make this more difficult than it is. It is not difficult. I'll let you know when it gets difficult. Give me 2 minutes. So what's the limit as x approaches negative 2 of our function 4x squared plus 3x minus 7? I don't know, right? We have to plug it in and see. So we get 4 times negative 2 squared plus 3 times negative 2 minus 7. Okay. So I don't know if you can see, right? This is just a combination right, of our, so we have our constant function here. We have a identity function with a constant multiple. And then we have, right, identity function with the power law and a constant multiple. So we're going to get 4 times 4 minus 6 minus 7, 16 minus 6. I don't know why I'm doing arithmetic in front of you. 10 minus 7 is 3. Okay, so the limit of this function as x gets close to -2 is 3. What about the limit as x approaches 0 of this rational function? So again, I've got a division, I've got a constant, I've got an identity, I'm adding them, right? I got a sum law going, I've got a difference law going, a constant, right? All of my limit laws are contained in here, right? I don't have anything else funky happening. So that's going to be equal to, right? We're just going to plug in the 0. So 12 times 0. Yeah, I don't know if you're like, well, what about 0 in the fraction, Angela? Okay, I know, but I'm not making the whole fraction 0. I'm just making parts of it 0. And as long as it's not the denominator in its entirety, then I'm good. So that looks like that value is -10/7. Okay. And then finally, what's the limit as x approaches a of 6x squared plus 2x plus 1? What do you suppose we're going to do? Exactly. We're just going to plug in a. So this is equal to 6a squared plus 2a plus 1. Okay, so that's when, right, everything is nice and we can just plug it in and we don't get any, like, problems. But it's time for the difficult part, and it's not that difficult. There are 3 strategies that we're going to look at if we try to, right, evaluate a limit by substitution, but we get to division by 0. Okay, so if we try to, right, evaluate a limit with substitution and we come up with division by 0, then we have some strategies we're going to try. So the first one, the first example I have, what's the limit as x approaches 5 of this rational expression? All right, so we try to plug in 5. I'm not sure what happens on the numerator because I'm being lazy, but I see that I definitely get division by 0. That's going to be a problem. Okay, so what are we going to do? Well, let's see. The first thing we'll try is, can we factor and reduce, right, this fraction, right? Can we reduce this rational function? So let's take a second. And we're going to use, right, our clue here. So this is a limit, x approaches 5, x minus 5, right? It would be helpful if I had a factor of x minus 5 in the top so that I could cancel. So we're going to hope that this is, right, a true math problem. So if x minus 5 is 1, let's see, it'd have to be a 2x and a 3, and that would have to be plus. I'm just doing a guess check here. What do I get? -10 plus 3, that's -7. Yay, it worked. So take a minute here. It's like, okay, I'm canceling these 2 factors. What I'm saying is, and I'm going to write this down here because I'm going to come back up and finish. So pause, come down here. 2x squared minus 7x minus 15 over x minus 5 is equivalent to 2x plus 3, exactly the same. My voice is still up, I'm not done. These 2 expressions are exactly the same for all x. Here's a new symbol, right? This is, if you're taking notes and you're trying to keep up, this is what we write for the phrase for all. So upside down capital A. So these 2 expressions are exactly the same for all x that are not equal to 5. So the value at x equals 5 is the only piece of information that we lost when we reduced. Okay. Every other value is exactly the same. Okay. And for limits, believe it or not, the only value I don't care about is at 5, is at a. I'm only looking at the values close to 5, but not necessarily equal to 5. So I'm fine if they, right, if these 2 aren't the same at x equals 5, as long as they're the same close, like, or everywhere else. So like at 4.9 or 4.99, right? They're the same there. Same exact y value comes out regardless of which one I plug into. Okay, so let's go ahead and figure what we get. Now I can evaluate this by substitution. So that limit is 2 times 5 plus 3. So that's 13. So I wanted to show you these on the graphs of these two different functions. So let's look at, and if you have your calculator there, go ahead and plug these in. So in y1, I want to plug the rational expression version. And in y2, we're going to plug the simplified version. Okay? And then change your window so that you can see stuff that happens around x equals 5. So I'm going to move my paper. I'm going to put my calculator, y equals, and clear that out. Okay, so what do I have there? 2x squared minus 7x minus 15 divided by x minus 5. And y2, I'm going to put the linear one plus 3. I'm going to check my window because I had it set up for other things. So I'll go -5 to 10. Oh gosh, I really don't, it's 5. I don't know what kind of y values I'm going to get out here. So I'm just going to go -10 to 10 just to see. Oh wait, scale 1. Thank you. I might have to change my window because my y window because I really am not sure what I'm going to come up with. Well, that's not good. I don't think I got my division in there correctly. Did you guys see that? Did I miss my division? Hold on, let me hit my y equals again. Oh, I did. I absolutely did. I don't have the x minus 5 for my bottom. They were supposed to be the same graph. Okay, let's try again. Okay, so there's my blue graph, my y1. 2x squared minus 7x minus 15 over x minus 5. Oh, look, there's the red line going right on top of it, exactly the same. But now what I want you to do is I want you to evaluate both functions at x equals 5. Okay? So the way we're going to do that is we're going to go on your calc. So second calc. And we're going to do the value. And let's do x equals 5. Okay, so depending on what version of your calculator you've got. So mine, up here at the top of my screen, I have y sub 1 equals, and it tells me that I'm on the rational function version, right? And here's my x equals 5, and in the y equals, it's blank. I've got no y equals. If I want to see what it gives me for y sub 2, I think I'm just going to hit my down arrow and hopefully it changes my function. And it does. So now, right, it's in red. So y sub 2, 2x plus 3 if x equals 5, y equals 13. Okay, so it wasn't there for 5, but it is, or it wasn't there for 5 on the rational function graph, but it is there, right, once we've reduced it. Okay. So factor and reduce, especially right if you've got a fraction and you get division by 0. Okay. Strategy 2, if one of your pieces happens to be a radical, a square root, what you can do is multiply by the conjugate, right, of the term with the square root in it. So remember what the conjugate is? Same two terms, different sign. So what I'm going to do is, I'm going to go ahead and do a little workspace down here. So I'm going to come up with an equivalent expression. Oh, and by the way, I'm sorry, I should have checked. Why don't you just plug it in? You should always check to see if you can just evaluate with substitution, right? I was getting ahead of myself because I wrote the problem, so I knew what I was going to get, right? But if we try the x equals 4, I'm going to get division by 0 down here on the bottom. So I knew it, I was anticipating. Sorry. Okay, so I'm going to start with the expression we have, and we're going to manipulate it in such a way that I get something I can just plug the 4 into. So I want to multiply by the conjugate of the, right, in this case, the numerator, because that's the one with the radical. So conjugate, same two terms, different sign in the middle. square root x, and a 2, opposite sign. Now I'm trying to create an equivalent expression, so that means I can only multiply by 1. So that whatever I did to the top, I'm going to do to the bottom. So I multiply the top by square root x plus 2. I'm going to multiply the bottom by square root x plus 2. So here we go. Go ahead and multiply. Those are binomial, so remember to FOIL or whatever your strategy is. So in the numerator, I'm going to get, let's see, square root x times square root x is x. When you multiply by a conjugate, you can go ahead and write it out for a couple of times, but you'll probably get tired of that. But the outer and the inner, right, have opposite signs. So those always add out. And then I have a minus 4. For your denominator, I'm actually not going to FOIL it. Don't FOIL, because I want to be able to cancel this x minus 4. Oh my gosh, and looky what we have here, a factor of x minus 4 in the top. Is it always going to work like that? Well, you know, if it gets written right so that you have something to do. So again, I multiplied by 1. I'm creating an equivalent expression. Go ahead and reduce that fraction. 1 over square root x plus 2. This expression is exactly the same as the one we started with for all x's. Right, so these are exactly the same for all x not equal to 4. So if I look at my alternate version, I'm going to take the limit as x approaches 4 of 1 over square root x plus 2. This is one I can evaluate by plugging in the value 4. So square root 4 plus 2, so that looks like 1/4. Right? So if you graph the original function, in the vicinity of x equals 4, it looks like your y value is headed towards 1/4. Okay, finally, strategy 3, if you have a complex fraction, right, a fraction within a fraction, sometimes if you simplify it, right, something nice will happen and it'll get to a place where you can evaluate by plugging in. So we'll go ahead and try the evaluation, but again, I wrote the problem, I know what's coming. So if I evaluate the limit as x approaches -3, I'm going to get 0 in the bottom. Division by 0 can't do that. So we're going to go ahead and simplify that complex fraction. So there, right, whatever your strategies are, and if you don't have any, you can watch mine, and if you need more, go on YouTube and Google simplify complex fractions. So I'm going to, what am I going to do? I'm going to multiply top and bottom by x plus 2. It's not the only strategy for simplifying a complex fraction, but it's the one that I typically go to. Okay, so the denominator is now x plus 3 times x plus 2. And the numerator, this x plus 2, multiplies both pieces that were in the numerator, so it's going to distribute. So it's going to multiply the 1, and it's going to multiply, right, that 1 over x plus 2. So that's going to become, stay with me, so the x plus 2, when it multiplies the fraction, right, I'll show you. So that's an x plus 2, right, that's the one we brought in, x plus 2, the denominator that started. And then I have x plus 2 times 1, so that's just an x plus 2. I don't think that orange is showing up super awesome, so I'm going to go ahead and I'll go back to blue. Well, x plus 2 over x plus 2, right, that's just 1. Keep with me here, so now I've got a 1 plus x plus 3 over, sorry, plus 2, getting ahead of myself, over x plus 3 times x plus 2. I still have not multiplied those out because I'm hoping for a miracle or a math problem. X plus 3 for the top. Yay, x plus 3 times x plus 2 for the bottom. Oh, look, scratch, scratch, 1 gets left behind. So I now see that the complex fraction I started with is equivalent to the expression 1 over x plus 2, right? Again, for all x not equal to negative 3. So now I can plug negative 3 into this thing because that does not cause me grief. And it looks like I'm going to get a negative 1 for my answer. So in general, if you cannot evaluate a limit with substitution, we're going to reach into that algebra toolbox and try to figure out some way you can manipulate your function so that you can plug in your a value. Okay, so these are the 3 most common strategies: factor, multiply by a conjugate, or simplify the complex fraction.